Hello, my name is Mike and I'm excited to present our work, Iterative Repair of Social Robot Programs from Implicit User Feedback via Bayesian Inference. Creating natural interactions for social robots is challenging. It requires tedious and error-prone tuning of interactive program parameters per each robot's user who may change their behavior over time, demanding to repeat the whole tuning work again. Our goal is to facilitate fluent and autonomous social robot behavior authoring with an expressive yet maintainable approach. To that end, we propose an iterative program repair process. It starts with a programmer writing a transition function program of a finite state machine representing the robot behavior. We introduce a domain-specific language that lets programmers to use holes in place of low-level details such as sensor value thresholds and timing parameters, specified as probability distributions. When ready, the program is executed on the robot and the robot's user interacts with it. The system collects the interaction trace, such as FSM inputs, outputs, and states that are occurred during the interaction. If the holes are set to bad values, interaction breakdowns are likely to happen. For example, just now the robot should have waited for the user but moved on to the next question and made her to tap the go back button. We assume a recovery mechanism like go back or next buttons as shown in this video is available, and hence the user can fix the breakdowns and continue interacting with the robot by themselves. Once the interaction is over, the programmer can easily annotate breakdowns offline by correcting the mismatches between the expected and recorded state trace. Alternatively, such corrections can be derived from the user's recovery inputs, freeing the programmer from the remaining repair process. The repair algorithm now uses the corrections to improve the program by estimating the hole distributions. The process is iterative, and hence our repair algorithm uses a Bayesian inference technique to efficiently update the distributions as more corrections become available. To systematically evaluate the proposed Bayesian repair algorithm, we created human simulators for sampling a large number of FSM input and ground truth state traces. We also created a more traditional search-based repair algorithm to use it as a baseline method. We then compared the two algorithms over 3 social robot interaction scenarios over 5 repair iterations. We measured the interaction quality of each algorithm using percentage overlap between the ground truth and the repaired program's state trace. We also measured the algorithm speed using repair time. Our results show that the proposed algorithm performs nearly identical in percentage overlap measure in all 3 scenarios. In terms of the speed, it outperforms the baseline as the Bayesian repair time remains at constant while the baseline repair time increases linearly over the iterations. To test the full pipeline, we conducted human experiment with 10 participants and a custom-built social robot. The participants interacted with the robot over 4 iterations. We present one example from our qualitative results. The video shows one participant participating in the question and answer interaction scenario. When the participant stopped speaking, the robot failed to detect her floor management gaze inversion and moved on to the next question, breaking the interaction and left her seemingly frustrated. After the 2 repairs, the program was able to detect the participant's floor management gaze aversion and waited until she completely finished answering the question. We present the full results, discussions, and future work in our paper. Thank you for listening.